So today, for differentiation, we have the power rule, we have the product rule, and now today we add to it the quotient rule. And so our quotient rule basically says that if f and g are differentiable, and assuming that g of x isn't 0, then if we're doing the derivative of f divided by g, then it looks like this. So we have the bottom times the derivative of the top function, and then minus the derivative of the bottom times the top. Now, the order, I can write f prime g here, and I could write f g prime here, but since this is subtraction this time, unlike the product rule, it doesn't matter in which order I write them. And then this is actually, doesn't look very good there. This is actually g, plain g, squared. Okay, so I just want to demonstrate, again, this isn't a proof. The proof is in the book if you would like to see it. This isn't a proof, but I wanted to just show you that we can use this in both directions and get the same thing. So h, if I simplify it, is really 1 over x squared, which I could write as x to the minus 2. So h prime of x, using our power rule, is negative 2 x to the minus 3. Or without a negative exponent, I could write it as negative 2 over x cubed as my h prime. So this time, just to show that it works, let's use the quotient rule here with h being x over x cubed. So my h prime of x will be, okay, so I'm gonna assume that this is f on top and this is g on the bottom. So g is the bottom, so that's x squared, or x cubed, I'm sorry, times the derivative of the top, f prime, so the derivative of x is 1, and then I have minus, now g prime, so g prime, g is x cubed, so that would be 3x squared. If you don't know how to do these derivatives quickly, then you should go back and rewatch that lecture on the power rule. And so the last thing we have is f, and f is the top, so that is x. And then in the bottom, we have g squared, so the x cubed quantity squared. All right, so if I open up my parentheses here, my h prime is x cubed, since x cubed times 1 is x cubed, minus 3x squared over x to the 6th. Oops, I'm sorry, that should be a 3 here, because I have x squared times another x, and I end up with negative 2x cubed over x to the 6th. Now it doesn't look exactly the same yet, but I can simplify this, right? I have an x cubed in the top, I have an x to the 6th in the bottom, so 3 of these x's, it's like x times x times x, will simplify with 3 of these x's, leaving me with negative 2 over x to the 3rd, right? Which is in fact the same, right? So when you see a quotient, it's not the derivative of the top divided by the derivative of the bottom, it's the quotient rule, which says you have the bottom times the derivative of the top minus the derivative of the bottom times the top all over bottom squared. So there's a couple of different rules that you can, there's some sort of, I don't know, ways to remember this. And so if you think of f being the high function and g being the low function, then some people say low d high, meaning the derivative of the high function minus high d low, right? F is high, d the derivative of the low function over low or low squared. So I kind of remember it in terms of g. It sort of looks like g 1 2. So however you want to remember it, just remember it. But the order does in fact matter, right? With the product rule, it's just the derivative of one times the other plus then the opposite. But for the quotient rule, it's very similar. It's just that the order does matter, where it's always the bottom times the derivative of the top going first. Okay, so let's use this. So I have f, and we're going to just find derivatives here. We're going to use f prime of x is equal to, I guess I'll write these out just like I did with the product rule a couple times just to get the swing of it. I'm not going to do that forever, but maybe in this lecture I will. So it's the bottom times the derivative of the top, so I'm not doing the derivative, I'm just putting it in place, minus then the top times the derivative of the bottom, So this time that one gets the derivative mark all over the bottom squared. All right, so now I just need to. I'm not going to simplify again either. I'm just going to drop everything into place and leave it alone. So I have x squared plus 1 times 5, the derivative of 5x minus 2, minus, then the 5x minus 2 doesn't happen to anything to that, then times the derivative of x squared plus 1, which is 2x, over x squared plus 1 quantity squared. And that's my derivative. Yes, I definitely could simplify the top, and in some cases when we get further on we will, but never ever do we ever multiply out this denominator. Usually if we're going to do anything, it's to factor and simplify, and this is already factored. So we never want to expand the denominator. Now the top, sometimes we do. We'll expand it and simplify it, but never the denominator. All right, so let's find g prime. So g prime of x, I'll write it out again. It's the bottom times the derivative of the top, just saying what I'm going to be doing, and then minus the opposite, this time the derivative of the bottom times the top, all over x minus 3 quantity squared. Now I would like to caution you, those of you who really like to simplify things, when I use this quotient rule, right, because I always get the bottom times the derivative of the top, right, the bottom, and then I get the over the bottom squared, I have lots of students who think, oh yeah, simplify. No, no simplifying here, because this minus sign means that if I'm going to simplify it from here, then I have to simplify it from here. This isn't x minus 3, right, this is the derivative of x minus 3. So be very careful of those of you who want to simplify things. All right, so this time I'm going to just drop the derivatives in place, so I need to change this and this. Everything else will remain the same. X minus 3, the derivative of x squared minus 4 is 2x, minus the derivative of x minus 3 is just 1, so I'm not actually going to write that, and then I'm just going to have x squared minus 4 here, all over x minus 3 quantity squared. And since I'm not doing anything else with this, I'm just leaving it like it is. Okay? Again, if I was going to do anything, maybe I would multiply together the top, but never ever I wouldn't expand the bottom. I would just leave it alone. Okay, so let's use all of this newfound knowledge to find the equation of the tangent line. Okay, so an equation of a line, remember, is y minus y1 equals m times x minus x1. And so we need the slope and a point. So we have the x-coordinate of the point, right? We have this so far, and we need m. Okay, so just a reminder, so I find the y-coordinate by plugging 1 into my f, right? So f of 1 over here is 3 minus 1 squared, which is 1, all over 1 plus 5. So I end up with 2 over 6, or 1/3. That's my point. And my m, remember, my slope of my tangent line is the derivative at that point. So my m is f prime of 1. So just dropping in what I know right now, I have y minus 1/3 equals f prime of 1 times x minus 1. Now I need to replace this f prime of 1 with the actual value. All right, so this time I'm going to need the quotient rule, okay? So I'm just going to kind of write out the quotient rule. I'm not going to write all the in-between steps. So I've got the bottom, make sure you use parentheses here, times the derivative of the top. So I have 3 minus x squared. So the derivative of the top would be minus 2x. All right, and then I have minus, then the top times the derivative of the bottom. The derivative of the bottom is 2x plus 5, all over x squared plus 5x quantity squared. All right, now we could simplify, we definitely can, but all I'm going to do is pop in 1 everywhere, and so whether I simplify or not, assuming I do everything correctly, I'll still get the same value. That's why it's not terribly important that I simplify. So f prime of 1 is going to be, So when I plug in 1 here, I get 1 plus 5, right, times I plug in 1 there and I get negative 2. And then I have minus 3 minus 1, because 1 squared is still 1. And then I have 2 plus 5 all over 1 plus 5 quantity squared. I'm just plugging in 1 everywhere there's an x. So 1 squared is 1. Okay. So my f prime of 1 is equal to 6 times negative 2 minus 2 times 7 over 6 squared. So this is equal to negative 12 minus 14 over 36. So I have negative 26 over 36. These are both, oops, I'm sorry. Okay, so I'm just have 6 times negative 2, that gives me negative 12, minus 2 times 7, which is 14, over 6 squared, which is 36. So I have negative 26 over 36, which means I have negative 13 over 18. And all I have to do, it doesn't matter if it's a fraction, I'm just popping it back in here. That's my f prime of 1 is negative 13 over 18. So in my last step I have y minus a third equals negative 13 over 18 times x minus 1. I didn't really need parentheses around this piece, but this is my equation of my tangent line. Right? That's why point slope is just beautiful, because I don't even have to combine any fractions or anything. Alright, so one more example. At what point on the graph, or points on the graph, of f of x equals 2x minus 1 over x squared would the tangent line be horizontal? So first of all, let's decide what that means. Okay, so if a tangent line is horizontal, right, that's horizontal, then what slope does it have? It has a slope of 0. So this question is asking me, at what point is the slope of my tangent line equal to 0? And the answer to that question is the solution to f prime of x is equal to 0. Okay, so again, I can use my handy-dandy quotient rule. So my quotient rule tells me I have the bottom times the derivative of the top. The derivative of 2x minus 1 is 2. Then minus, now I have the top times the derivative of the bottom, which is 2x, all over x squared. So here's my derivative. Now this time I am going to set it equal to 0, so I'm going to clean it up a little bit. So I have 2x squared minus, let's see, I'm going to think of it like this, minus 2x times 2x minus 1, and distribute here. So I have negative 2x times 2x, which gives me negative 4x squared, and then negative 2x times negative 1 gives me plus 2x over x squared. All right? So I'm going to plug in 0 here now in this step, and my last step here, I can simplify these, they're like terms. I have negative 2x squared plus 2x over x squared. All right, so this will be equal to 0, right? My first step here, I can just multiply the x squared by both sides, and I immediately get 0 equals negative 2x squared plus 2x. I notice that there is a common 2. I'll factor out the negative as well, and an x, leaving me with x minus 1. Oops, sorry about that. All right, so in this step, I multiplied x squared, right? I did here and here. It canceled on this side, leaving me with this, and then 0 times x squared is 0. Now I'm left with this, and I factored out a minus 2 just because I don't like when my leading coefficient is negative. So I factored out a negative 2 and an x. So negative 2x times x gives me negative 2x squared. Negative 2x times negative 1 gives me positive 2x. And so now I get an x equals 0, and an x minus 1 is 0. It gives me x equals 1. Now we're going to throw out x equals 0. Maybe you can guess why, right? What's my original function? Aha, right? What's my domain restriction here? x can't be 0, right? It's always, those domain restrictions are always lurking in the background. So I can't use that one. It's not a solution to my equation. So that means that at x equals 1, f prime of 1 is 0. And so it asks for the point, and so I have the x coordinate, and so now I just plug in. So basically my point will be 1 f of 1, right? And so I have f of 1, I'm plugging it in up here. So it would be 2 times 1 minus 1 over 1 squared. Right? That's plugging it in here, 2x minus 1 over x squared. 2 times 1 minus 1 over 1 squared. So f prime, or actually this is plain f of 1, is 2 minus 1 over 1, and I end up with 1. So at 1, 1, the slope of my tangent line is in fact horizontal. Okay, another rule down.